Welcome everyone. Thanks for staying awake. Today I would like to tell you about our latest simulation work in the field of gas discharge physics. This work has been done here at the Wigner Institute with collaboration with Zoltán Juhász from Veszprém. The story starts at the International Space Station. Well, surely you know there are several experiments up there which utilize the microgravity environment. One of those experiments is a dusty plasma experiment called PK4 from the German plasma crystal sphere. It's located at the European Science Module, and this is how it looks inside. Of course, it's all shielded in a closed cover. The experiment utilizes a gas discharge, which is very similar to that here on the lighting, or as that in the old-fashioned advertisement signs, the neon signs. It is actually a neon discharge. It is a direct current discharge. That means one of the electrodes, which is here, is grounded, and the other one is driven by a constant voltage. And the trick here, that's a schematic sketch of the experiment, is that here in the central region, they introduce dust particles. With dust particles, I mean small spheres of melamine formaldehyde, which is a plastic. Monodisperse spheres, typically in the size range, they have several different sizes between 2 and 12 micrometers in diameter. Those dust particles interact with the gas discharge. In the gas discharge, you have free electrons and ions. The dust particles get charged, negatively charged in this case, and they interact with each other through the Coulomb force and form a system, an interacting many-body system, which has the advantage that each and every dust particle can be monitored, can be followed with CCD cameras. So you have a many-body system where you actually have the full trajectories of every particle. I mean, thousands of particles you can follow in this system, and have the full mechanical information of the velocities and positions as a function of time. And that's what people do. So these are actual images from these experiments. Of course, the dust is illuminated from the side with a laser, and then the cameras capture the scattered light, scattered laser light. And a few experiments, for example, using a manipulating laser, you can push the particles and introduce flows and streams and manipulate the whole dust cloud and study on the kinetic level what's happening in such a system. There was one thing that was not expected but was observed, mainly that the dust particles tend to align into elongated chains parallel with the discharge tube. This is kind of puzzling because, yes, there are known mechanisms for this formation of chains, because, I mean, you should see these are all negatively charged particles. So in principle, if the interaction was purely Coulomb repulsion, then they should settle in kind of zigzag geometry. Everyone wants to be as far as possible from the others. Obviously, long chains is not the optimum configuration for that. But there are known phenomena that can cause this. One of them is if you have your negatively charged dust particle in a plasma, which again consists of negative electrons and positive ions, plus, of course, lots of neutral atoms, then it's called plasma screening. Everything you put into the plasma will screen it. So you have a negative dust particle, it will repel the electrons and attract the ions, so it will form a kind of screening cloud around itself, which is called the Debye sphere. And usually it is really spherical. It is a screening sphere. But of course, if you want to have ion drift, a significant drift of the ions in the plasma, that will distort this screening sphere. It will be kind of ellipsoid. It will develop a dipole moment. And if we now imagine a second dust particle sitting here, it will feel the repulsion from the other dust, but it will also feel the attraction to this positive space charge cloud. And if we use alternating electric field, and with this alternatingly induce ion drift in both directions, alternatively we can induce quadrupole moments in this field. Another mechanism is also known, it is called ion wake field, where the ions which move very fast next to the negative dust actually get focused as they pass this attractive center. The ions get focused below the dust particle, and again, if you have one more dust particle, it will be attracted by this field. So these are known mechanisms for chain formation, but both of these mechanisms need high speed ions, high drift velocities. But the BK4 discharge is a DC discharge, a long one, and if you open any gas discharge textbooks from 100 years ago up to now, you will find that this part of the gas discharge where these particles are sitting and are observed by the cameras is called the positive column. And in the positive column region, the electric field is very low. And with this, the ion drift is very low. So the ion drift is, for these mechanisms, you need ion Mach number above 1. So the ion drift velocity compared to the sound speed in the environmental plasma. Or here you need a so-called thermal Mach number, where the ion drift velocity compared to the thermal velocity of the ions is large. In all cases, for normal positive column conditions, this is much lower than 1. So we don't know why this is happening. Our tool that we use to investigate this, to explain why this is observed, is a so-called particle and cell with Monte Carlo collisions technique. Particle and cell technique is a pretty standard technique in particle simulations. You follow your particles, they move in an external field, you solve their equations of motion, and self-consistently, as they are charged particles, they modify the space charge. So you solve the Poisson's equation to get the new electric field after you moved one time step. The tricks to accelerate simulations is that, of course, you don't take into account all the 10 to 14 electrons which are in such a volume and a discharge. You use superparticles instead of real particles. So let's say you represent 100,000 electrons by one simulation particle, one superparticle. And you don't take into account pairwise interactions with each seeing the other one, but you work on a numerical grid. You calculate the electric field, electric potential on the grid. This is the cell part, so particle in cell. And the particles interact with the electric field, which you compute on the grid based on the based on the boundary conditions and the space charge of the particle. So it's self-consistent in a way. That was the big part. Monte Carlo collision part is a little more tricky one. The electrons and also ions are accelerated by the electric field, and they have a large chance to hit one of the background atoms, neon atoms in this case. So they can, after one time step, you have to decide, did collision happen or not? If there was a collision, was it an elastic collision, just scattering, or was it an inelastic collision? If it was an inelastic collision, was it excitation? To which level? Was it an ionization? If there was ionization, you have to create a new ion and a new electron, take it into the particle pool, and continue with the new particles as well. So there are lots of ifs and branching and random numbers in this process, because all these decisions are made based on measured statistical quantities like collisional cross-section data, but by using random numbers. So at the very beginning, I was really afraid to go to parallel. We use these simulations for a decade or more on CPU serial codes. And of course, we also realized that parallelism is the way to go if you want to harvest the power in your hardware. But with all this branching and particle creation and annihilation and the loss and all these things, it seemed to be tricky, and maybe it still is. But at the end, it worked. And actually, I'm pretty happy with it. So first, I will show you the physics results, what we give as a plausible explanation for the chain formation. And then I can go into some details of the code. So first of all, This is a picture from the actual experiment at the space station. They have the camera showing the middle part of the discharge. You saw it was actually banded, but it doesn't really matter. They just image the central part. It is the positive column. So this part here. So let's put that. So we set up the simulation, just throw in some random electrons just to start the process, and then in one day you get something like this. Negative electrode, positive electrode, glass tube, and that's all. All the rest is self-consistently built up by the particles, by the space charges. If you open a textbook again, DC discharge, you see negative dark space, negative glow, Faraday dark space, positive column. All the global structure of the discharge just appears by the simulation. There's nothing of this is imposed in the code. It just comes out. And if we do data acquisition for long, I mean 1 millisecond is long. I mean it's a long simulation, and just average over this time. But actually what you see is the excitation source. So this should correlate to the light that you see if you switch on the discharge. Then we got very similar structure than what was observed in the experiment. In the experiment, they use a camera which has an exposure time of 10 milliseconds. But if we reduce the averaging time and take short snapshots of the structure of the discharge, we see this, exactly the same run. I let it run longer and average, and here I stopped after a microsecond. So obviously these two are different. The difference is in the time of averaging. So this is the same like this, just averaged over time. So these features are actually moving quickly. These are called ionization waves, and they do average out on the time scale where the experimental observation is done. If I place myself where the dust particles are sitting in experiments, so in the center, and just look in time what electric fields and what densities, charge particle densities I experience in my environment, then this is shown below. So the key feature is here. The electric field which the particle experiences, the dust particle, and its environment is, well, by far not smooth and averaged. You have actually peaks which are 10 times higher than that of the time average. So the textbook, if you open and you say it's 2-3 volts per centimeter, the field in the positive column, that's the time average. But it is composed of large peaks with 10 times higher amplitude. So this, of course, if I tell at the beginning that small electric field is not enough to accelerate the ions, it's true, but these peaks may be already large enough to accelerate the ions to high enough velocities to have higher Mach numbers. But is this true, or is this just numerical artifact? So what I can do is time, position, and the center of the tube, and again showing you the light emitted by the discharge. You see nicely how, I mean, the slope of these are the phase velocities of the phase wave fronts. We have nice collaborators in Texas. Actually, of course, each instrument which is up in the space station, you have ground-based replicas to perform test experiments. One is at Baylor University, Texas. After this, I told them, make some images with your fast camera. So this camera makes 50,000 frames per second. And look at this. To me, this is exactly the same. All the features, lower slope, larger slope, transient region, are all there. Even in the transient region, you have a higher intensity, then you have a kind of jump. It's all tiny features match between experiment and simulation. And again, here the simulation was first and had predictive power. Little time, particle-based simulation. In the simulations, we use a few million particles. The grid size is a long tube, so cylindrical geometry. Grid is usually in this size of a few hundred times 4,000. Neon gas with all its quantities like threshold energies and cross-section data. And we use the CUDA language to accelerate it on GTX cards. And as I showed you the circle, this iteration diagram, there are several steps. And of course, optimum is if you can implement all of them on the GPU, because then you don't have to move data in all time steps to switch between CPU and GPU. And actually, I guess we achieved that. So we have the Poisson solver, which is relatively standard thing, different methods, but it's standard. The particle pusher means that you move the particles in one time step, move them away. Then, of course, in each time step, you have to collect all the densities, because that you need for the Poisson solver. So you have to reduce reduction and get all the particle positions and form a density distribution on the grid, because that's the input for the Poisson solver. That's also done. We have to search for the data for the cross-section data, for the collision data is a numerical form, measured points. So we have to interpolate that. Also, there's random number generator. We wrote our own based on numerical recipes, and all the rest, except particle removal is on CPU, but that has to be done only after several thousand time steps. Poisson solver is really easy. Black and red successive over relaxation. The solver itself is this single line. The rest is just setting the indexes. This is, of course, an iterative method, so you have to monitor the accuracy and define a threshold of error which you can still accept. The random number generator, again, very simple. We simply took it from the numerical recipes as the suggested one. Of course, this is the single precision version, which is not the suggested one. The suggested one is, of course, the double precision version, but this is the second best they can provide. Again, very simple. There's one trick which goes against general knowledge. I mean, high-performance computing people always say, use structure of arrays instead of arrays of structures, because for vectorization, this is much better. Well, maybe not in this case. So we have particles. Each particle have positions, velocities, something collision states, something for the Monte Carlo routine. Each particle carries with it the random seeds. And as in each particle movement step, each it's not here. Maybe it's not here. No, it's not here. So in the pusher algorithm, where you make the one time step for the particles, move them one time step, all this is loaded in the shared memory for each thread. Each thread is taking care about one particle, so it's a particle decomposition. Loads this in the shared memory, does all the updates, use this information, use it for the random number generator for everything, and then at the end it writes it back to the global memory. And this is all at one place. So for me, it looks very logical to take this, whatever, 100 bytes, put it in your shared memory and work with it and put it back, instead of having, I don't know how much is this, 16 or whatever, arrays, and then we just spread around in the memory. So this looks to be working, but of course, that's what Zoltan is doing. That's more collaboration basis of a collaboration, that someone needs to optimize this. Because this is, the last slide, about performance. It I just simply naively count how many operations I have in the kernels, multiply or divide with the time, runtime, which MV profile tells me. Then I get performance numbers in the 200 gigaflops on the card, which on the 1080 Titan card, which has the theoretical maximum of 5 teraflops. So we are, which I would say, if we reach 500 to 1,000 gigaflops, that is the maximum. Due to this branching, due to this random numbers and the different scenarios for different particles, it is absolutely hopeless to reach even half of the theoretical maximum. But if we can reach, let's say, 20% of it, that would be already a state where no more optimization would be needed. But we are still not there, so that's still needed. But anyway, if you don't care about those numbers, the real thing is here, that our previous code, which does similar things, needed 3 months on an MPI parallel version to converge, and now I need 1 or 2 days. So that's the main difference that matters to me. Thank you.
question.
So you told us that the simulation was running from different time periods,
Yes.
if I understood it correctly, but I assume you are using discrete time steps.
Yes.
How did you find out which is the correct time step?
A time step has to be chosen to resolve the fastest motion in the plasma, which is in this case the electron plasma frequency, which is in the order of 10 to 9 radians per second or 1 per second. So the time step is chosen to be 10 to minus 12 to resolve all natural oscillations of the charged particles. So it's always, we check always, if it's a magnetized system, we check for cyclotron frequencies, plasma frequencies, and always use enough to resolve the fastest of those.
Thank you.
Any other short questions? Yes, one more.
Is there any benefit in trying to use the axial symmetry to also simplify the momentum space, or you actually need that you have discrete particles and momentum space doesn't have axial symmetry anyway?
No, the momentum space does not have, so it's a 2.5 dimensional simulation, cylindric in geometry in space, but 3-dimensional.
Yeah, I saw that, but I'm curious whether there's any benefit in trying to, because there's only one angle, am I right?
Yes, so the azimuthal angle doesn't matter. We tried at earlier times, but actually found that converting back and forth, because for the collision angles, where you have a collision, you have to define new collision angles, where you have lots of sine and cosine and all these things. We always ended up with going to Cartesian coordinates, where you have the 3, and
so you didn't see anything?
I didn't see any, no benefit.
Let's thank Péter again.